Where does a black hole get its gravity from? Sit with that question for a moment, because it is stranger than it sounds. A black hole has, by definition, no surface, no matter you can point to. Whatever fell in is gone, sealed behind a boundary that light itself cannot climb back out of. And yet a black hole pulls harder than almost anything in the universe. It bends the paths of stars 1,000 times its size. It warps light around itself like a lens. It holds entire galaxies in orbit around a single dimensionless point. So where is that pull actually coming from if there is nothing left to do the pulling? Physicists have an answer, and it is far stranger than the mass is still in there. It involves a theorem that says black holes have no hair. It involves a boundary made of pure geometry. It involves the unsettling possibility that gravity was never coming from the matter at all. Get comfortable. Hit subscribe if you're new here, because by the end of tonight, the thing you thought was the simplest fact about a black hole is going to feel like the strangest one. Now let's slowly ease into this. The pull that outlives its source. Picture the sun, not as a symbol, not as a yellow circle in a child's drawing, but as the actual object. A ball of plasma 1.3 million times the volume of the Earth, so massive that its gravity holds 8 planets, a belt of asteroids, and a cloud of comets in orbit across 4 billion miles of empty space. Every one of those planets stays in its lane because the sun is there, physically, continuously, every second, made of matter that has mass, a mass that curves the space around it. Remove the sun, and the pull disappears with it. That is how gravity is supposed to work. No source, no field. It is the most basic intuition you carry about the universe, and you have carried it since before you could talk. Things pull because they are there. Now take that same amount of mass, roughly 1 solar mass, and imagine compressing it. Not gently. Not the way a star quietly cools and contracts over billions of years. Imagine crushing it past the point where anything we call matter can be said to still exist in any conventional sense. Past the density of a white dwarf, past the density of a neutron star, where a teaspoon would weigh 1 billion tons. Keep going. At some threshold, the compression becomes unstoppable. Nothing known to physics can hold the collapse back anymore. The material does not simply become extremely dense. It falls past every flaw that density is supposed to have, and it does not stop falling. What is left, according to general relativity, is a boundary in space called an event horizon, and behind that boundary, mathematically, a singularity, a point of technically infinite density where the equations of physics simply stop producing sensible answers. We will spend real time later tonight on what that singularity might or might not physically be, because the honest answer is that nobody knows, and that not knowing is one of the most important open wounds in all of theoretical physics. But set that aside for a moment and focus on something simpler and, in its own way, even stranger. Whatever is or is not happening at the singularity, the horizon around it is not the edge of a physical object the way the surface of a star is the edge of a physical object. It is a boundary defined purely by geometry, by the shape of space-time itself. There is no wall there. There is no material shell you could theoretically dig into. It is simply the last radius from which light can still climb outward. 1 inch closer, and even light, moving at the fastest speed anything can move, cannot escape. 1 inch farther, and it can. And here is the part that should genuinely stop you. The the part this entire episode is going to spend 2 hours pulling apart thread by thread. Outside that horizon, the gravity is exactly what you would calculate for the original mass. If the Sun were somehow replaced this instant by a black hole of the same mass, Earth's orbit would not change, not even slightly. We would go dark, colder than anything in human history, but we would keep orbiting the same point in space, at the same distance, on the same track, for the same reason. The pull would be identical. A black hole formed from a collapsed star exerts precisely the gravitational force that star exerted when it was a star, blazing and enormous and unmistakably there. Sit with that, because it is not a minor detail, it is the whole mystery in miniature. The star had a surface, it had a boundary you could point a telescope at and say, there, that is where the matter is. That is the thing doing the pulling. The black hole has no such thing. Cross the horizon, and by every serious model we have, you are not approaching a smaller, denser version of a star. You are approaching a region where the very language of approaching a location starts to break down. And yet from outside, nothing about the gravitational signature has weakened even slightly. The force is there. The orbit is there. The bending of starlight around it is there, precise to the decimal point predicted by Einstein's equations. The pull persists exactly as strongly as it did when there was, by any ordinary definition, something there to pull. This is where most casual explanations quietly wave their hands. They will tell you, correctly, that mass curves space-time, and that the black hole still has mass, so of course it still has gravity. That is true. It is also almost entirely unhelpful, because it dodges the actual question. Mass curving spacetime is a description of what happens. It is not an explanation of the mechanism, of the physical process by which a specific chunk of matter, sitting at a specific location, reaches out across the void and bends the path of a star 10 million miles away. For an ordinary object, you can at least tell yourself a story about how that happens. The sun is there, its atoms are there, and general relativity says that stress and energy, wherever they are located, dictate the curvature of the space-time around them. There is a source, and there is a field the source generates continuously, moment to moment, the way a magnet continuously generates a magnetic field for as long as the magnet exists. But inside a black hole, the there gets complicated in a way it never does for a star. Depending on which framework you take seriously, and we are going to walk through several of them tonight, the matter that fell in either continues collapsing forever toward a singularity that may or may not be a real physical place, or it stops making sense to talk about the matter as a located object at all, somewhere well before that. And crucially, none of this uncertainty about what is happening inside changes the gravitational pull measured outside by even 1 part in a trillion. The books balance perfectly on the outside, no matter what chaos or absence or breakdown of ordinary physics is happening on the inside. That disconnect, that a black hole's gravity is completely, precisely, unshakably determined from the outside, while the actual physical status of the source is genuinely unknown and possibly unknowable, is not a minor curiosity buried in a physics textbook footnote. It is one of the central open problems connecting general relativity, thermodynamics, and quantum mechanics. And it has occupied some of the sharpest minds of the last 100 years. Karl Schwarzschild found the first exact solution to Einstein's equations for a collapsed mass within weeks of Einstein publishing General Relativity in 1915, while serving on the Russian front during the First World War, calculating artillery trajectories by day and solving the equations of the universe by night. He did not live to see what his solution implied. He died the following year, and it would take decades before physicists were willing to take his mathematics literally, before they stopped treating the horizon as a mathematical inconvenience and started treating it as a real feature of a real object hanging in the sky. Tonight, we are going to take it exactly that literally. We are going to ask, carefully and patiently, where a black hole's gravity actually comes from once the object that supposedly caused it can no longer be located in any conventional sense. We are going to meet the no-hair theorem, a result so strange it sounds like a joke until you see the mathematics behind it. We are going to meet the idea that a black hole's entire gravitational identity might be written not in its interior at all, but smeared across its horizon, a two-dimensional surface encoding a three-dimensional pull. We are going to ask what Newton would have made of an object whose gravity persists after its matter, in any meaningful sense, does not. And we are going to end somewhere genuinely strange, at the edge of an idea that suggests gravity itself everywhere, all the time, including right now in the chair beneath you, might be a kind of illusion generated by information on a boundary you can never reach. But first, we need to understand exactly what falls apart and what survives when a star collapses. We need to meet the theorem that tells you a black hole is, in a very precise sense, the simplest object in the entire universe. Part 2. The theorem that erases everything. Imagine, for a moment, that you could design a star. You choose its composition down to the isotope. You choose whether it is built mostly of hydrogen or carbon or something stranger. You paint a pattern across its surface, a swirl of sunspots, a scar of magnetic loops, a lopsided bulge where it is not quite spherical. You give it a particular history, a particular chemical fingerprint that any sufficiently good telescope could read from its spectrum and use to reconstruct in broad strokes the entire story of how that star came to be. A star is a librarian's dream. It is dense with information, and almost all of that information sits out in the open, written into the light it emits. Now collapse that star into a black hole and watch what happens to all of that information from the outside. It disappears. Not fades, not blurs, disappears, completely and totally, in a way that has no analogue anywhere else in physics. This is the finding at the heart of what physicists call the no-hair theorem, developed through the combined work of Werner Israel, Brandon Carter, David Robinson, and Stephen Hawking across the late 1960s and early 1970s. And it is one of the strangest, most restrictive results ever proven about any physical object. The theorem states that once a black hole settles down, once it has finished ringing from whatever violent collapse or merger formed it, its entire external gravitational and electromagnetic signature can be described, completely and exactly, using only three numbers: its mass, its spin, and, if it happens to carry one, its electric charge. That is the entire library. Three numbers. Not the composition of the star that collapsed. Not whether it was made of hydrogen or of something far stranger. Not the shape of the collapse, the asymmetries, the sunspots, the magnetic field structure, the isotopic ratios, the chemical history. Any of it. Physicists chose the word hair for all of that extra detail specifically because hair is exactly the kind of surface feature that distinguishes one otherwise similar object from another. The texture and colour and pattern that make an individual recognizable. A black hole, the theorem says, is bald. Two black holes with the same mass, the same spin, and the same charge are not merely similar. They are identical in every externally measurable way, indistinguishable in principle by any experiment anyone could ever perform from the outside, no matter how sophisticated. It does not matter if one formed from the collapse of a star made almost entirely of iron, and the other formed from the collision of two black holes that themselves formed from stars made of nothing but hydrogen. Once they finish settling into their final state, once the theorem's conditions are satisfied, they are the same object. There is no experiment, even in principle, that could tell them apart. Stop and feel how strange that actually is, because it is easy to hear it as an abstract mathematical curiosity and let it slide past you. Nothing else in the universe behaves this way. A star retains chemical signatures for its entire life that tell you what it was made of, when it formed, what it has swallowed since. A planet keeps a geological record. Even a rock keeps an isotopic fingerprint that a sufficiently careful lab could use to reconstruct where it came from and what it has been through. Information in essentially every other physical system we know tends to persist, distributed messily across the object, recoverable in principle if you look closely enough. The no-hair theorem says that a black hole is the one object in the universe that structurally, provably, forgets, not approximately. Not as a practical limitation of our instruments, provably as a mathematical consequence of Einstein's equations themselves. And this is precisely where the gravity question sharpens into something genuinely uncomfortable. Because if a black hole's entire externally measurable identity really does reduce to just mass, spin and charge, and if mass is the single quantity most directly responsible for the strength of its gravitational pull, then the gravity we measure from outside a black hole cannot, in any meaningful sense, be coming from the specific matter that fell in. It cannot be tracking the individual protons and electrons and photons that once made up a star, the way you might imagine gravity as some kind of accounting system that keeps a running tally of every particle's location and contribution. Whatever mechanism is generating that gravitational pull has already thrown away every detail about the source except a single scalar number. The pull is real. It is precise. It follows Einstein's equations exactly. But the thing generating it appears to have been stripped down by the physics itself to almost nothing at all. This raises the question that will thread through the rest of tonight's exploration, and it is worth stating plainly here at the start, because everything that follows is an attempt to answer it from a different angle. If a black hole retains only 3 numbers about its source, where, physically, are those 3 numbers actually stored? Not stored in some abstract mathematical sense, but stored somewhere real, somewhere a physicist could point to and say, there, that is where the information that determines this object's gravity actually lives. There are, broadly, 2 candidate answers, and they pull in almost opposite directions, and both of them are taken seriously by working physicists today. The first answer, the one that feels more intuitive if you have absorbed the idea of a singularity from popular science documentaries, is that the mass is still there, still located at or extremely near the singularity, still functioning as a genuine source of gravitational field in exactly the way the sun's mass is a genuine source of its gravitational field. Under this view, the black hole's gravity comes from the same place any object's gravity comes from. There is simply a very small, very extreme region deep inside the horizon where all that mass energy still physically resides, still curving the space-time around it moment to moment, the way it always has. The horizon is not a wall that stops the source from existing. It is merely a one-way boundary that stops light and information from escaping outward. Underneath the equations, on this view, nothing especially mysterious is happening. Mass is where it always was. Mass generates curvature. And we simply cannot see it directly because of a geometric feature of space-time rather than because the mass has somehow ceased to be a source. The second answer is much stranger, and it comes not from classical general relativity at all, but from a very different corner of theoretical physics, the study of black hole thermodynamics and the deep. Disorienting connection that emerged in the 1970s between black holes, entropy, and information. Under this view, the horizon itself is not merely a boundary that hides a source elsewhere. The horizon is, in some profound sense, the source. The information that determines a black hole's mass, its gravity, its entire external behavior is encoded not at a singularity buried at the center, but smeared across the two-dimensional surface of the event horizon itself, the way a hologram encodes a three-dimensional image using only a flat, two-dimensional piece of film. On this view, asking where inside the black hole the gravity comes from is somewhat like asking where inside a hologram the three-dimensional image is stored. The question contains a hidden assumption that the information must be located at some interior point, and that assumption may simply be false. Both of these pictures are live options in modern theoretical physics. Neither has been definitively ruled out, and reconciling them, working out precisely how they relate to each other, is one of the deepest ongoing projects in the search for a theory of quantum gravity. Tonight, we are going to walk through both of them properly, in detail, and we are going to see exactly why each one, taken seriously, leads somewhere genuinely disorienting. But to understand either answer, we first have to go back to Schwarzschild's desk in the winter of 1916, on the eastern front of a war that would eventually kill him, and understand exactly what he found when he solved Einstein's equations for the very first time, and why the strange boundary he discovered took physicists nearly half a century to take seriously as a physical object rather than a mathematical accident. Part 3. The Soldier Who Solved the Universe from a Trench. In the winter of 1915, Albert Einstein published the field equations of general relativity, 10 interlocking equations of extraordinary complexity describing how mass and energy curve the fabric of space and time. They are, even today, notoriously difficult to solve exactly. Most real-world situations require approximation, simulation, brute computational force. Einstein himself did not expect an exact solution to arrive quickly, if ever. It arrived within about 2 months, from a place no one would have predicted. Karl Schwarzschild was a German astrophysicist, already accomplished, already respected. And in late 1915 he was serving as an artillery officer on the Eastern Front of the First World War, calculating the trajectories of shells for the German army. In the gaps between that grim, practical work, using nothing but pencil, paper, and an extraordinary command of mathematics, he took Einstein's newly published equations and found an exact solution describing the spacetime around a single, perfectly spherical, non-rotating mass. He mailed his result to Einstein from the front. Einstein, by his own account, was astonished that anyone had found an exact answer so quickly, and personally presented the paper to the Prussian Academy of Sciences on Schwarzschild's behalf. Schwarzschild contracted a rare autoimmune skin disease at the front and died the following spring in May of 1916, at just 42 years old. He never lived to see what his own solution actually meant. What Schwarzschild's solution described, once physicists worked through its full implications, was this. Around any spherical mass, there exists a specific radius, now called the Schwarzschild radius, at which the mathematics does something extraordinary. For the Sun, That radius is about 3 kilometers. For the Earth, it is about 9 millimeters. If you could somehow compress the entire mass of the Earth down into a sphere the size of a marble, the mathematics says that at that 9 millimeter boundary, the equations describing spacetime curvature stop behaving normally. Time appears from the outside to slow to a stop. Light aimed directly outward from that boundary does not escape. It hovers forever, neither rising nor falling, trapped at the exact edge of no return. For decades, this was treated by most physicists, including Einstein himself, as a mathematical curiosity rather than a description of anything real. There was a very reasonable argument for dismissing it. Ordinary matter, the thinking went, simply could not be compressed to that extreme. Something would always intervene. Electron pressure would halt the collapse of a dying star the way it does in a white dwarf. And if electron pressure failed, surely some other force, not yet fully understood, would step in before the star reached anything resembling Schwarzschild's boundary. The radius was seen as a kind of mathematical horizon in the truest sense. A line the equations described perfectly, but that nature sensibly would never actually let anything reach. That confidence began to erode in 1930, when a 20-year-old graduate student named Subrahmanyan Chandrasekhar, on a long sea voyage from India to England, worked out the mathematics of what happens to a white dwarf star as you increase its mass. He found that there was a limit, now called the Chandrasekhar limit, at roughly 1 4/10 times the mass of our Sun, above which electron degeneracy pressure, the quantum mechanical effect that normally holds a collapsing star up, simply could not do the job anymore. Beyond that mass, nothing in the physics of the 1930s could explain what would stop the collapse. Chandrasekhar's own mentors, most notably the towering figure of Arthur Eddington, publicly ridiculed the idea in front of the Royal Astronomical Society, calling it, in essence, a stellar absurdity that nature would surely find some way to prevent. Chandrasekhar was, in the end, entirely correct, and it would take decades and considerable personal cost to him before the physics community fully accepted it. He won the Nobel Prize for the work in 1983, more than 50 years after he first derived it as a young man on a ship. The next crucial piece arrived in 1939 from Robert Oppenheimer and his student Hartland Snyder, working at Berkeley. They asked a very specific, very careful question. Set aside whether such extreme collapse ever actually happens in nature, and simply ask what Einstein's equations predict happens to a sufficiently massive ball of matter once it starts falling in on itself with nothing left to hold it up. Their calculation, simplified but rigorous, showed something remarkable and deeply unsettling. To an observer watching from a great distance, the collapsing star appears to slow down as it approaches the Schwarzschild radius, its light growing redder and dimmer, seemingly freezing at the boundary, never quite crossing it. Not even after an infinite amount of outside time has passed. But to an observer imagined as riding along with the collapsing matter itself, falling inward with it. Nothing dramatic happens at that boundary at all. They cross it in a perfectly ordinary, finite amount of their own time, feeling nothing special in that instant, and continue falling inward toward whatever lies at the centre. That split, that a boundary can be simultaneously an infinite wall from one perspective and a smooth, unremarkable threshold from another, is one of the most genuinely mind-bending features of general relativity, and it is the reason it took physicists so long to agree on what the boundary even was. Was it a real physical edge, a place where something happens? Or was it an illusion of coordinates, a trick of how you choose to describe the geometry? no more physically real than the way lines of longitude appear to converge and become singular at the Earth's poles, despite the poles being perfectly ordinary places to stand. The answer, worked out carefully over the following decades, is that the horizon is not a true singularity at all. It is what physicists call a coordinate singularity, an artifact of the particular mathematical description Schwarzschild originally used, not a place where the actual physics breaks down. Using better coordinate systems, developed independently in the late 1950s and early 1960s, physicists showed that an infalling observer really does pass smoothly through the horizon, feeling nothing locally unusual at the moment of crossing, at least for a sufficiently large black hole. The true singularity, the place where the equations genuinely do produce infinities, where curvature, tidal forces and density all diverge toward the mathematically undefined, sits deeper inside, at the very center. The horizon itself, despite its dramatic reputation, is geometrically unremarkable from the inside. It is only unremarkable in a very particular sense, though, because once you cross it, every future directed path, every possible trajectory available to you or to light or to anything at all, leads only further inward. The horizon does not hurt you when you cross it. It simply, permanently removes the possibility of ever turning around. It was the physicist John Wheeler in 1967 who gave this entire class of object its now famous name, black hole, during a lecture at NASA's Goddard Institute, after a member of the audience suggested the phrase. Before that, physicists used clumsier language, collapsed star, or the more technical gravitationally, completely collapsed object. The new name stuck almost instantly, in part because it captured something essential in just 2 words. Black, because no light escapes. Hole, because it is, in a very real sense, a puncture in the fabric of what is causally connected to the rest of the universe, a region you can fall into but never climb back out of, regardless of how powerful your engines are, regardless of how cleverly you plan your escape. By the early 1970s, the mathematics of black holes had been worked out with extraordinary rigor by physicists, including Roger Penrose, Stephen Hawking, and others, and the object had gone, within a single scientific generation, from a suspicious curiosity in Einstein's equations, doubted by Einstein himself, to a rigorously understood, mathematically inevitable consequence of general relativity applied to sufficiently massive collapsing matter. What remained genuinely mysterious, what remains genuinely mysterious even now, was not whether black holes exist. Observational astronomy has settled that question beyond any reasonable doubt. Through decades of X-ray binary studies, through the direct imaging of the shadows at the centers of the galaxy M87 and our own Milky Way, through the extraordinary confirmation delivered by gravitational wave observatories detecting black holes colliding across billions of light years. What remains mysterious is something more fundamental. It is the question we started with tonight, sharpened now by everything we have just walked through. Once matter crosses that horizon, once it is causally severed from the rest of the universe by a boundary that even light cannot climb back out of, what, precisely, continues to generate the gravitational field that we measure, with total confidence and total precision, from safely outside? To answer that, we need to go inside, as far as the mathematics will honestly let us, and confront the singularity itself. And we need to ask a question that sounds almost childishly simple, and turns out to be one of the hardest unsolved problems at the intersection of gravity and quantum mechanics. Is the singularity a real place? Or is it the sound Einstein's equations make when they finally break? Part 4. The point that is not a place. Let's go back to the film we used once before tonight, Run in Reverse. Except this time, we are not rewinding the whole universe. We are rewinding a single collapsing star, watching it in your mind's eye, falling in on itself faster and faster as its own gravity overwhelms whatever pressure once held it up. The outer layers fall first, then the layers beneath them, all of it converging toward the center, the density climbing past anything a laboratory could ever produce, past the density of a neutron star, past 1 billion tons per teaspoon, past every threshold anyone has ever measured for anything. And according to the pure mathematics of general relativity applied without modification, the collapse simply does not stop. Ever, there is no flaw. The equations predict that all of that mass converges toward a single point of zero volume and, in the idealized, perfectly spherical case, infinite density. This is the singularity, and it sits, by prediction, at the very center of every black hole, hidden behind the horizon, permanently walled off from any observer on the outside. Now, you might reasonably suspect that this is simply too extreme a prediction to take at face value, that it is exactly the kind of edge case where a theory, however successful elsewhere, is bound to be revealing its own limitations rather than describing anything physically real. That suspicion turns out to be exactly the right instinct, and it is worth understanding why physicists themselves share it, and why they nonetheless cannot simply wave the singularity away. In 1965, Roger Penrose proved something that took the singularity from being a curious feature of one idealized, perfectly symmetric solution to being an essentially unavoidable consequence of gravitational collapse in general. Using a technique involving what he called trapped surfaces, regions of space where all light rays, even ones aimed outward, are forced inward by the curvature around them, Penrose showed that once a collapsing star forms such a surface, and it needs remarkably mild, physically reasonable assumptions to do so, a singularity of some kind is essentially guaranteed to form. It does not require perfect spherical symmetry. It does not require any special or delicate configuration of the collapsing matter. Any sufficiently compact, sufficiently massive object, collapsing under gravity with no exotic escape hatch, is forced by the mathematics itself toward a singularity. Stephen Hawking extended this reasoning, together with Penrose, over the following years, showing that a closely related argument applies to the beginning of the universe itself. The same mathematics that traps a collapsing star also traps the entire cosmos, run backward in time, into a singular beginning. The two results are, in a very real sense, mirror images of each other, one about the deepest interior of a black hole, the other about the deepest past of everything. So the singularity is not an accident of a simplified model. It is not something that goes away once you account for a slightly lumpy, rotating, imperfect star instead of a perfect mathematical sphere. It is, within the framework of pure general relativity, essentially inevitable. And yet, and this is the crucial turn, almost no physicist working in this area today believes that the singularity is a real physical thing that actually exists. A genuine point of infinite density sitting inside every black hole in the universe. The reason is simple, and it echoes something we touched on with the singularity at the beginning of time itself. In physics, infinity is almost never a measurement of the world. It is, overwhelmingly, a signal that your theory has been pushed past the domain where it is valid, that you are asking it a question it was never built to answer. General relativity is a theory of smooth, continuous curvature. It describes gravity beautifully, with a precision that has been tested to extraordinary accuracy. From the bending of starlight during a solar eclipse to the exquisitely detailed timing of binary pulsars, to the direct detection of gravitational waves from colliding black holes. But it is, fundamentally, a classical theory. It knows nothing about quantum mechanics. And as you approach the singularity, the region of space you are describing becomes smaller and smaller, eventually approaching scales where quantum effects, which general relativity simply does not include, should become not just relevant, but dominant. There is a specific scale where physicists broadly agree this breakdown must occur, called the Planck length, an almost unimaginably small distance, roughly 100 billion times smaller than a proton. Below that scale, our current theories offer no reliable description of space-time geometry at all. Long before a collapsing star's matter reaches anything resembling a true zero-volume infinite density point, it should pass through that Planck scale threshold into a regime where gravity and quantum mechanics both matter simultaneously and where general relativity, on its own, has nothing meaningful left to say. This is where the story becomes genuinely open, genuinely unresolved, in a way that should feel less like a failure of physics and more like the exact place where the next great idea in physics is waiting to be found. Because if the true singularity, the mathematical point of infinite density, is not physically real, then something else must be happening in that deepest interior region instead, something that our current theories cannot yet describe, and there is no settled consensus on what that something is. There are serious candidates, and it is worth walking through a few of them, not because any one of them is confirmed, but because seeing the range of possibilities helps make clear just how open the question actually remains. One family of proposals, growing out of loop quantum gravity, suggests that space-time itself becomes granular, discrete, at sufficiently small scales. The way we discussed in the context of the universe's rotation earlier this year on this channel, and that this graininess produces a kind of quantum pressure that halts the collapse before it ever reaches true infinite density. Under this picture, sometimes called a Planck star, the collapsing matter reaches an almost unimaginably dense but still finite state, bounces, and begins expanding again, its collapse effectively reflecting off the smallest possible scale of space itself. Because of the extreme time dilation near the horizon, that bounce, from the outside, could take an almost unimaginably long time to become visible, which is one reason this idea remains difficult to rule in or out observationally. A second family of proposals, developed independently by several groups of theorists over the past 2 decades, suggests something even stranger, that the interior of a black hole is not a region of collapsing matter converging toward a point at all, but is instead filled almost entirely with a strange, stable configuration of quantum mechanical vacuum energy, sometimes described using the term gravastar, short for gravitational vacuum star. Under this picture, there is no singularity and, in some versions, not even a true horizon in the strictest sense. Only something that looks almost identical to a black hole from any distance we could ever measure, while hiding something categorically different underneath. A third, related idea, developed by theorists including Samir Mathur working within string theory, proposes something called the fuzzball. Under this picture, what looks from outside like empty space all the way down to a central singularity is in fact filled, edge to edge, with an extraordinarily complex horizonless structure made of strings and higher dimensional objects called brains. A structure so intricate that it effectively replaces both the singularity and, in a subtle but important sense, the horizon itself. The fuzzball, its proponents argue, is not merely a curiosity, It is an attempt to directly address a separate, equally profound puzzle we are going to spend real time on later tonight. The question of what happens to information that falls into a black hole, and whether it is truly lost forever or must somehow be preserved. None of these ideas has been confirmed. None of them can currently be tested directly, because the interior of a black hole, by definition, is causally sealed off from any measurement we could perform from outside. This is not a temporary limitation of our telescopes. The way the boundary of the observable universe is a limitation we might one day partially work around with cleverer instruments. It is a limitation built directly into the geometry of the object we are trying to study. And yet, remarkably, none of this deep uncertainty about the interior changes the central puzzle we opened tonight's episode with, not even slightly. Whether the true state of the collapsed matter is a genuine singularity, a Planck star, a gravastar, or a fuzzball. The gravitational field measured from outside is in every single one of these competing pictures identical. Every candidate theory of the interior has been carefully constructed, precisely because it must be, to reproduce the exact same external gravity. Governed by the exact same handful of numbers the no-hair theorem tells us survive. Which means the question we are chasing tonight cannot actually be settled by figuring out what is happening at the singularity, whatever it turns out to be. The gravity outside is completely indifferent to that answer. It is, in a very real sense, overdetermined, fixed, and unshakable long before physicists have any hope of resolving what is really happening in the deepest interior, which pushes us toward a genuinely different way of asking the question. Instead of asking what is producing the gravity from inside, perhaps we should be asking something stranger. Perhaps we should be asking whether the horizon itself, the boundary, the surface, rather than the interior, is where the answer has been hiding all along. And to get there, we need to leave general relativity behind for a moment and step into a completely different branch of physics that almost by accident in the early 1970s discovered that black holes behave in every measurable respect like objects that are unmistakably, undeniably, thermodynamically hot. Part 5. The object that should not have a temperature. In the early 1970s, a graduate student at Princeton named Jacob Bekenstein noticed something that seemed, on its face, almost absurd. He was thinking about a very old, very fundamental principle in physics called the second law of thermodynamics. The same principle we touched on earlier this year when we talked about why time flows in only one direction. The second law says, in its simplest form, that entropy, a measure of disorder, of the number of ways a system's microscopic details could be arranged while still looking the same from the outside, can never decrease in a closed system. It can stay the same. It can go up. It can never go down. This is one of the most inviolable rules in all of physics, tested more thoroughly and violated less often than almost anything else we know, and Bekenstein realized there was a problem, and it was a problem specifically about black holes. Imagine you take a box full of hot gas, full of entropy, full of disorder, and you drop it into a black hole. From the outside, that entropy is now gone. It has vanished behind the horizon into a region no observer outside can ever access, measure, or account for again. If the black hole itself carries no entropy of its own, if it is, as the no-hair theorem seems to suggest, an almost embarrassingly simple object defined by just mass, spin, and charge, then the total entropy of the universe, as far as any outside observer could ever measure it, would have just decreased. The disorderly gas is gone. Nothing disorderly appears to have taken its place. The second law of thermodynamics, one of the most sacred rules in all of physics, would seem to have been quietly broken simply by throwing something into a black hole. Bekenstein's proposed solution was audacious. He suggested in 1972 that black holes must themselves carry entropy, real physical entropy, and that this entropy must be proportional not to the volume of the black hole, the way entropy behaves for essentially every other physical system we know, but to the area of its event horizon. This was, at the time, a genuinely strange claim, and it met real resistance, including, notably, from Stephen Hawking himself, who initially found the whole idea somewhat absurd. If a black hole has entropy, Hawking pointed out, then by the basic logic of thermodynamics it must also have a temperature. And if it has a temperature above absolute zero, then by the same basic logic it must radiate, must glow, must emit energy outward, the way anything with a non-zero temperature does. But a black hole, by definition, by the very geometry that makes it a black hole in the first place, cannot let anything escape across its horizon, not even light. The idea seemed to contain a direct, built-in contradiction. Hawking set out, by his own account, intending to prove Bekenstein wrong. What he found instead. In a calculation published in 1974 that remains one of the most celebrated results in 20th century theoretical physics, was that Bekenstein had been essentially correct, and that the mechanism making it possible was even stranger than either of them had anticipated. Hawking applied quantum field theory, the framework that describes how particles and fields behave, not in flat, empty space, but in the curved space-time that exists right at the edge of a black hole's horizon. And he found that the horizon is not, in fact, a perfectly quiet, perfectly inert boundary. Due to the strange behavior of the quantum vacuum in strongly curved space-time, particle-antiparticle pairs are constantly, spontaneously appearing near the horizon. The way empty space itself is constantly seething with such pairs even far from any black hole, popping into existence and immediately annihilating each other, undetectable in ordinary circumstances. Near a horizon, though, something different can happen. Occasionally, one particle of such a pair falls inward, across the horizon, forever lost to the black hole's interior, while its partner escapes outward into the observable universe as real, detectable radiation. To a distant observer, this looks exactly like the black hole itself is emitting particles, glowing faintly, radiating energy outward into space. This is Hawking radiation, and the temperature associated with it, now called the Hawking temperature, turns out to depend, with startling simplicity, on nothing more than the black hole's mass. Larger black holes are colder, smaller black holes are hotter. A black hole with the mass of the Sun would have a temperature of roughly 60 billionths of a degree above absolute zero, so cold that it is utterly undetectable against the background warmth of the cosmic microwave radiation that fills the universe. But a sufficiently small black hole, one with the mass of a mountain rather than a star, would be blisteringly hot, radiating itself away in a final explosive burst. And here is where the two threads, Bekenstein's entropy and Hawking's radiation, tie together into something genuinely profound. Because the energy carried away by Hawking radiation has to come from somewhere, and the only place it can come from, given that nothing new is falling in, is the black hole's own mass. Which means that every black hole in the universe, given enough time, is very slowly evaporating, radiating its mass away, shrinking, imperceptibly for anything of stellar mass or larger, over timescales that dwarf the current age of the universe by almost incomprehensible margins, but shrinking nonetheless, following a process that is, in every meaningful thermodynamic sense, identical to a hot object cooling by radiating heat into its surroundings. Bekenstein and Hawking's combined result, now formalized as the Bekenstein-Hawking entropy formula, is one of the most quietly remarkable equations in all of physics, and it is worth sitting with what it actually says. Because the strangeness of it does not announce itself immediately. The entropy of a black hole, this vast reservoir of hidden scrambled information about everything that has ever fallen in, is exactly proportional to the area of its event horizon, measured in units of the Planck length squared, divided by 4. Not the volume, the area. Pause on that, because it deserves to be paused on properly. For every other physical system we have ever studied, entropy scales with volume. A box of gas with twice the volume, filled at the same density, has roughly twice the entropy, because there is simply twice as much room for the microscopic particles inside to be arranged in different ways. This is such a deeply ingrained expectation in physics that it barely gets stated explicitly. More volume, more possible arrangements, more entropy, it is almost tautological. A black hole breaks this rule completely. Double a black hole's radius, and its volume increases, roughly, by a factor of 8. Its surface area, however, increases only by a factor of 4, and its entropy tracks the area, not the volume, meaning a black hole's capacity to store information, its entropy, scales with the square of its size rather than the cube. For a sufficiently large black hole, this means that the amount of information the object is capable of holding is, counterintuitively, vastly smaller relative to its volume than the amount of information an ordinary object of the same size could hold, packed with ordinary matter arranged in ordinary ways. In fact, it can be shown, through a related argument developed initially by Bekenstein, that a black hole represents the single densest possible way to store information for any given surface area. Anything you could imagine that stores more information than a black hole's entropy allows, packed into a region bounded by that same surface area, would necessarily be so dense that it would already have collapsed into a black hole itself. This single, strange fact that entropy and information scale with the surface area of the boundary rather than the volume of the interior is not a minor mathematical footnote. It became, over the following 2 decades, the seed of one of the most radical ideas in the history of theoretical physics, an idea that reaches far beyond black holes and, if it is correct, applies to the entire universe, including the empty space around you right now as you listen to this. It is called the holographic principle, and it says, in essence, that everything that can ever happen within any given volume of space, every possible configuration of matter and energy, every possible history, is completely, exactly, and losslessly encoded on the boundary of that region, on a surface with one fewer dimension than the space it contains. The universe, this principle suggests, might be something like a hologram, a flat, 2-dimensional recording that we experience, from the inside as a rich, detailed, 3-dimensional world. And this, finally, brings us back to the question we have been circling since the very first sentence of tonight's episode. If a black hole's entropy, its capacity to store information about everything that has fallen into it, lives on its horizon rather than in its interior, then perhaps its gravity does too. Perhaps the mass, spin and charge that the no-hair theorem tells us are the only surviving fingerprints of a collapsed star are not, in fact, sitting at a singularity deep inside, patiently generating a gravitational field that radiates outward through the interior and across the horizon. Perhaps they are, in some far stranger and more literal sense than physicists originally intended when they first started using the word, painted directly onto the horizon itself. A boundary of pure geometry that is not merely hiding the source of the black hole's gravity, but is, in some deep and still not fully understood sense, the source. To understand just how seriously physicists have come to take that possibility and how far it now reaches beyond black holes into a proposal about the fundamental nature of gravity itself, we need to follow the holographic principle out of the black hole physics that birthed it, and into one of the most influential papers in the last 30 years of theoretical physics. Part 6. The Universe Written on Its Own Edge. In 1993, the physicist Gerard Hooft, already a Nobel laureate for his work on the Standard Model of particle physics, took the strange scaling of black hole entropy and asked a question that most of his colleagues considered, at the time, almost recklessly bold. If entropy near a black hole's horizon scales with area rather than volume, what if that is not a special quirk of black holes at all, but a clue about the deepest nature of physical reality itself? What if the amount of information that can exist within any region of space, black hole or not, empty room or not, is always fundamentally limited by the area of the boundary enclosing that region rather than by its volume? Leonard Susskind, working independently, developed the idea into a rigorous physical proposal shortly afterward and gave it the name it carries today, the holographic principle. The core claim is genuinely startling. Every physical process that can ever occur inside a given volume of space, every particle collision, every chemical reaction, the entire life story of every star that will ever form and die within that volume can in principle be completely and exactly described using information encoded on the boundary of that volume alone, a surface with one fewer spatial dimension than the space it contains. Our apparent three-dimensional universe, under this proposal, might be something closer to a projection, an experience generated from data that is, at some more fundamental level, two-dimensional. For years, this remained an elegant but largely unproven conjecture, a beautiful idea without a rigorous mathematical backbone. That changed in 1997 when the Argentinian physicist Juan Maldacena published a paper that is now among the most cited in the history of theoretical physics. Maldacena did not prove the holographic principle for our universe directly. What he did was something almost as remarkable. He constructed an explicit, mathematically precise example of exactly this kind of holography, working within string theory in a simplified, idealized universe shaped differently than our own, called anti-de Sitter space. He showed that a theory of gravity operating throughout the interior volume of this idealized universe is, in every respect that can be checked, mathematically identical to an entirely separate, gravity-free quantum theory living only on its boundary. Two completely different-looking descriptions, one with gravity and one without, one in 3 spatial dimensions and one in 2, turned out to be exact translations of each other, the same physics written in 2 different languages. This result, now called the AD-S-CF correspondence, gave the holographic principle its first rigorous mathematical proof of concept, and it has become one of the most productive tools in all of modern theoretical physics. Used today not only to study black holes, but to study the behavior of exotic states of matter in laboratories on Earth. Our own universe does not have the exact geometric shape that Maldacena's original proof requires, and translating the full holographic principle into a rigorous statement about our actual cosmos remains, honestly, unfinished work. But the conceptual lesson is one that most theoretical physicists working in this area now take extremely seriously, and it applies directly to the question we have been chasing tonight. Gravity, in this framework, is not simply one force sitting alongside the others. It appears to be something closer to a kind of illusion, a description that emerges when you take genuinely fundamental information, sitting on a lower dimensional boundary, and translate it into the language of a higher dimensional space. Gravity, on this view, is not something happening inside a volume. It is what a boundary looks like from the inside when you are standing in the space that boundary encodes. This brings the black hole question into sharp, strange focus. If the holographic principle is a real feature of nature and not merely a mathematical trick that works in idealized toy universes, then a black hole's gravity is not merely correlated with information on its horizon. The horizon, in a very real sense, is where the physical description of the black hole actually lives. The mass, spin and charge that the no-hair theorem preserves are not bookkeeping labels for something hidden deeper inside. They are properties of the boundary itself, and the gravitational field we measure from far outside the black hole is the three-dimensional experience of information that is, more fundamentally, encoded across a two-dimensional surface. This does not mean, it is worth being careful here, that there is literally nothing inside a black hole, that the interior is empty in any simple sense, or that an observer falling through the horizon would notice anything resembling a wall or a screen at that boundary. For a sufficiently large black hole, general relativity strongly suggests that an infalling observer crosses the horizon smoothly, feeling nothing dramatic in that moment, just as Oppenheimer and Snyder's original calculation showed back in 1939. The holographic description and the traditional interior description are meant to be two complete, self-consistent, and in principle equally valid ways of describing the exact same physical situation, not competing claims about which one is real and which one is fake. This equivalence, unsettling as it is precisely the point, and it goes by the name black hole complementarity, developed largely by Susskind, Gerard Hooft, and their collaborators through the 1990s. An observer who stays outside the horizon can, in principle, describe absolutely everything about the black hole using only information smeared across its surface. An observer who falls through the horizon experiences, instead, an ordinary interior, continuing to fall toward whatever genuinely lies at the center, whether that is a singularity, a Planck star, a fuzzball, or something we have not yet imagined. Both descriptions, remarkably, are believed to be complete and consistent on their own terms, and the deep, still unresolved puzzle at the frontier of this research is precisely how these two pictures, one holographic and boundary-based, one traditional and interior-based, actually fit together without producing contradictions that violate the basic laws of quantum mechanics. If you take this picture seriously, and a great many serious physicists now do, it offers a genuinely startling answer to the question this entire episode has been built around. Where does a black hole's gravity come from? Not, ultimately, from a singularity, hidden and inaccessible, quietly generating a field the way a hidden magnet generates a magnetic field. It comes, at the deepest level current theoretical physics can currently describe, from information. Encoded not somewhere buried at the center, but distributed in the most literal and mathematically precise sense we currently have, across the horizon itself, a boundary made of pure geometry that nonetheless behaves, in every measurable way, as though it is the true physical source of the pull. And if that is true for a black hole, an object whose gravity is unusually extreme and unusually well studied, the holographic principle suggests something far more radical still. It suggests that this same relationship, boundary encoding volume, might not be a special feature of black holes at all. It might be how gravity works everywhere, which means the question we open tonight with, stranger than it first appeared, might not really be a question about black holes specifically. It might be the sharpest, clearest version we currently have of a much larger question about the nature of gravity itself, one that some physicists now believe reaches all the way down to the chair you are sitting in and the floor beneath it, right now. Part 7. Gravity from nothing at all. If the holographic principle really does describe our universe and not merely a mathematically convenient toy model, then a question arises that reaches far beyond black holes, and it is worth sitting with slowly because it touches something you have taken for granted every single moment of your life. What if gravity itself, everywhere, not just around black holes but around planets, around stars, around the 2 bags of sugar you might hold in your hands a meter apart, is not a fundamental force at all? What if it is something that emerges, the way pressure emerges, from the collective motion of countless individual gas molecules? Or the way the smoothness of water emerges from the chaotic jostling of trillions of individual water molecules that are, on their own, nothing like smooth? This is not a fringe idea whispered at the edges of the field. It is a serious, actively pursued research program, and its most influential modern statement came from the Dutch physicist Erik Verlinde. In a paper published in 2011 that startled a great many of his colleagues, precisely because of how far it pushed the logic we have been following tonight. Verlinde proposed that gravity is what physicists call an entropic force, not a fundamental interaction transmitted by some particle in the way electromagnetism is transmitted by photons, but a statistical, thermodynamic effect, arising the same way an ordinary entropic force does in far more mundane systems. To understand what an entropic force actually is, it helps to leave gravity aside for a moment and think about something far more familiar, something you have felt with your own hands. Stretch a rubber band, it pulls back, resisting the stretch, wanting to snap back to its original shape. For a long time, physicists explained this the way you might naively expect, in terms of the energy stored in the stretched molecular bonds of the rubber. But that explanation, it turns out, is largely wrong, or at least badly incomplete. The real reason a stretched rubber band pulls back is mostly entropic. In its relaxed state, the long polymer chains that make up the rubber can coil and fold into an enormous number of different possible configurations, an enormous amount of disorder, an enormous entropy. Stretch the band, and you force those chains to straighten out, dramatically reducing the number of possible configurations they can occupy, reducing their entropy. And because the second law of thermodynamics relentlessly pushes any system toward higher entropy whenever it is free to move that way, the rubber band pulls back, not because of some direct mechanical tension in the ordinary sense, but because pulling back is, statistically, overwhelmingly, the more probable direction for the system's disorder to increase again. The force you feel in your fingers is not fundamental. It is a large-scale, emergent consequence of an underlying drive toward disorder that has nothing to do, at its root, with any force being directly transmitted between molecules. Verlinde's proposal is that gravity might work in an analogous way at the deepest level, though the reasoning involves a specific manner of counting information rather than the coiling of polymer chains. Building directly on Bekenstein's insight that entropy scales with area, Verlinde imagined dividing space up into a series of nested holographic screens, each one a kind of boundary encoding information about everything on one side of it, in exactly the spirit of the holographic principle we just walked through. When a mass moves near such a screen, he argued, it changes the amount of entropy associated with that boundary, and the universe's persistent statistical drive toward higher entropy, the same drive that pulls a stretched rubber band back, produces an effective force. Verlinde showed, remarkably, that when you work through the mathematics of this picture carefully, you recover something that looks, in the appropriate limit, exactly like Newton's familiar law of gravity, the same inverse square relationship that has correctly described falling apples and orbiting planets since 1687. Push the calculation further into a fully relativistic setting, and there is a real, if still contested, case to be made that you can recover Einstein's full equations of general relativity as well, not as fundamental postulates about the geometry of space-time, but as emergent, statistical, thermodynamic consequences of an underlying informational structure. If this picture is correct, then the question this entire episode has been circling. Where does a black hole get its gravity from? Dissolves into something even stranger than the answer we reached in the last part. It is not merely that a black hole's gravity is encoded on its horizon rather than generated at its singularity, distinct from ordinary objects like stars. It is that every object's gravity, everywhere, all the time, including your own body's gravity right now, pulling ever so faintly on the walls of the room around you, might work this same way. Mass, on this view, does not directly reach out and curve the space around it the way you were taught to picture it, the way a bowling ball sags a stretched rubber sheet in the popular illustration. Instead, mass changes the entropy associated with informational boundaries surrounding it, and the force we experience as gravity is the statistical, thermodynamic echo of the universe's relentless tendency to move toward higher entropy, expressed through geometry rather than through molecules, expressed as the bending of space-time itself rather than as the coiling of a rubber band's polymer chains, but arising from the same fundamental logic. It is important, in the spirit of intellectual honesty that has run through this entire series, to be precise about the current status of this idea, because it is genuinely, actively contested within the physics community, and pretending otherwise would do a disservice to how science actually works. Verlinde's original entropic gravity proposal has faced serious, substantive technical challenges since 2011. Several physicists have raised concerns about whether the specific derivation actually holds together rigorously, whether it can be extended cleanly and consistently to more general, less symmetric situations than the simplified cases where it was first demonstrated, and whether some of its later, more ambitious predictions, particularly a controversial 2016 attempt by Verlinde to use the same entropic framework to explain away the need for dark matter entirely, actually hold up against detailed observational data. That dark matter proposal in particular has, on balance, not fared well against the accumulated evidence, especially evidence from gravitational lensing in colliding galaxy clusters, of the kind we discussed at length in an earlier episode on this channel. Evidence that seems to require an actual, physically located, unseen mass rather than a purely emergent geometric effect. But here is what makes this area of physics so genuinely exciting to be alive for, rather than simply unsettled or unresolved. Even researchers who remain deeply skeptical of the specific technical details of Verlinde's 2011 proposal, and there are many serious, credentialed physicists who fall into exactly that camp. very often still accept the much broader, more foundational insight that grew directly out of black hole thermodynamics in the 1970s. The insight that connects Bekenstein's entropy formula to Maldaceno's holographic correspondence to the modern active research program often called it from qubit, a phrase coined by John Wheeler decades ago and taken up with renewed seriousness by a new generation of theorists working at the intersection of quantum information theory and gravity. That broader insight is this: gravity and geometry appear to be, at some deep level not yet fully understood, intimately entangled with information, with entropy, with the raw statistical bookkeeping of how many ways a system's underlying microscopic details can be arranged. Exactly how that entanglement works, whether gravity is fully emergent in Verlinde's specific sense, or whether it retains some more traditionally fundamental status while still being deeply and mysteriously connected to information in ways we do not yet fully understand, remains one of the most actively contested, most exciting open frontiers in all of theoretical physics. Which brings us back, one more time, to the black hole sitting quietly at the center of tonight's episode, patiently holding a star's worth of matter behind a horizon it will never release. If gravity really is, at bottom, a story about information and entropy rather than a story about matter directly reaching out through space, then perhaps the deepest, most honest answer to the question we opened with tonight is not that a black hole's gravity comes from its singularity, and not exactly that it comes from its horizon either, treated as some special, isolated object. Perhaps the answer is that gravity, everywhere in every object, was never really coming from matter directly at all. Perhaps it was always, quietly, coming from information, and a black hole simply happens to be the one object in the universe extreme enough, simple enough, and strange enough to finally force us to notice. Part 8. The paradox that would not stay solved. If a black hole's gravity really is tied to information encoded on its horizon, then a second question, quieter, but in some ways even more urgent, has been sitting underneath everything we have discussed tonight, waiting its turn. What happens to that information, eventually, once the black hole finishes evaporating? Hawking's own 1974 calculation, remember, showed that black holes slowly radiate their mass away, cooling and shrinking over unimaginably long timescales until, in principle, nothing is left at all. And Hawking radiation, as he originally calculated it, comes out looking almost perfectly random, a smooth thermal glow with no discernible imprint of whatever specific matter originally fell in to form the black hole, and no discernible imprint of whatever specific matter fell in afterward, book by book, star by star, across the black hole's entire lifetime. If that calculation is taken completely at face value, then once a black hole finishes evaporating entirely, all the detailed information about everything that ever fell into it, every atom's precise quantum state, every photon's exact history, appears to have been genuinely, permanently erased from the universe, replaced by nothing more than a diffuse cloud of thermal radiation carrying no trace of its origin. This should stop you because it directly threatens something that quantum mechanics treats as close to sacred. Quantum mechanics is at its core built on the principle that information is never truly destroyed, only ever scrambled, redistributed, hidden behind overwhelming complexity, but never actually deleted from the universe in a way that makes it impossible, even in principle, for a sufficiently powerful calculation to reconstruct the past from the present. This principle even has a name, unitarity, and it is arguably as fundamental to quantum theory as the second law of thermodynamics is to statistical physics. If black hole evaporation genuinely destroys information, then quantum mechanics itself, one of the two great pillars of modern physics, is not merely incomplete near black holes. It is, in some deep sense, simply wrong there. This is the black hole information paradox, and it is not a minor technical footnote. It has occupied some of the sharpest minds in theoretical physics for close to 50 years, precisely because it sits directly at the fault line between general relativity, which predicts the horizon and the evaporation in the first place, and quantum mechanics, which insists that information cannot simply vanish. Hawking himself, for decades, argued forcefully that information really is lost, a position that put him in direct, public, extended conflict with other leading physicists, including Leonard Susskind and Gerard Hooft, the very physicists whose holographic ideas we spent the last two parts exploring. The dispute became formal and dramatic in 1997, when Hawking and his collaborator Kip Thorne bet the physicist John Preskill that information really is destroyed in black holes, with the losing side agreeing to provide the winner an encyclopedia of the winner's choosing, from which information could, fittingly, be freely retrieved. In 2004, Hawking conceded the bet, publicly and somewhat dramatically, at a conference in Dublin, having become convinced, largely through the holographic reasoning developed by Susskind, Hooft and Maldacena, that information does in fact survive, encoded subtly within the correlations of the outgoing Hawking radiation itself, smuggled out not through some obvious single message, but through impossibly intricate quantum entanglement between individual particles of radiation emitted at different moments throughout the black hole's entire evaporating lifetime. He gave Preskill a baseball encyclopedia, chosen, Hawking joked, because he had hoped Preskill would find it as useless as information trying to escape a black hole. The gesture was as much a concession that his own earlier confidence had been wrong as it was a real payment. Conceding the bet, though, did not actually solve the problem. It merely clarified, with much greater precision, exactly how difficult the problem actually was. Because working out the specific mechanism, the concrete physical process by which information, trapped for the entire history of an evaporating black hole, eventually reappears, encoded in radiation that Hawking's original 1974 calculation suggested should carry none, has proven to be extraordinarily hard. And in 2012, a group of physicists, including Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, sometimes referred to by the initials of their surnames as AMPS, published a paper that reignited the entire debate in an even sharper, more uncomfortable form. Their argument, now known as the firewall paradox, showed that you cannot simultaneously preserve three things that most physicists had, until then, assumed could all be true at once. You cannot simultaneously have information genuinely escape in the Hawking radiation, exactly as unitarity demands, and have the horizon be a smooth, unremarkable boundary that an infalling observer crosses without noticing anything dramatic, exactly as general relativity has always insisted, going all the way back to Oppenheimer and Snyder's original 1939 calculation, and have ordinary quantum mechanics apply consistently everywhere outside the horizon, with no exceptions. Something, the AMP's argument showed with disturbing mathematical rigour, has to give. And one especially unsettling possibility they raised is that the smooth, gentle horizon predicted by general relativity might not actually be smooth at all, that an observer falling through it might not drift peacefully across a boundary that feels like nothing special, but might instead encounter a wall of extraordinarily high-energy radiation right at the threshold, a firewall, that would incinerate anything crossing it instantly, directly contradicting more than 70 years of confident theoretical understanding about what falling into a black hole should actually feel like. This debate remains genuinely, actively unresolved today, and it is a healthy thing, not a failure, that it does. Several promising proposals have emerged in the years since 2012, attempting to dissolve the paradox without resorting to a firewall. One influential line of work, developed by Maldacena and Susskind, proposes a striking conjecture sometimes summarized with the shorthand ER equals EPRA, suggesting that the quantum entanglement connecting particles of Hawking radiation to their partners still inside the black hole might be literally, geometrically identical to the kind of microscopic wormhole structure first identified mathematically by Einstein and Rosen back in 1935, connecting distant regions of space-time. Under this picture, entanglement and space-time geometry are not two separate things that merely happen to be correlated. They may be, at the deepest level, the very same underlying phenomenon described in two different mathematical languages, which would mean that the information trapped inside a black hole is never truly separated from the radiation escaping outside at all, connected instead by an unbreakable, purely geometric thread running directly through the interior. A separate breakthrough, arriving in 2019 and 2020 from several independent groups of theorists working with sophisticated tools borrowed from string theory, produced calculations using objects called replica wormholes, that for the first time actually managed to reproduce, from first principles, the specific curve that information theory predicts the entropy of Hawking radiation should follow. If information really is preserved throughout an entire evaporation, a curve known as the Page curve, after the physicist Don Page, who first derived what it should look like back in 1993. These calculations strongly suggest, though they do not yet constitute a complete, universally agreed upon resolution, that information genuinely does survive, smuggled out through extraordinarily subtle quantum correlations that Hawking's original, simpler 1974 calculation was never equipped to capture. What makes all of this relevant to tonight's central question, rather than a separate detour, is that every one of these proposed resolutions, the ER equals E pair conjecture, the replica wormhole calculations, all of it, reinforces the same picture we arrived at in the last two parts from an entirely different direction. They all point toward gravity, geometry, and information being far more tightly and inseparably bound together than classical general relativity, on its own, ever suggested. A black hole's gravity, its horizon, its interior geometry, and the information it swallows and eventually releases increasingly look, to the physicists working closest to this problem, less like four separate features of one object and more like four different faces of a single deeper structure that we do not yet have the complete language to describe. Part 9. What Newton could never have imagined he was missing. It is worth pausing here, more than halfway through tonight's journey, and doing something we have not done yet. Stepping all the way back, out past the horizons and the holograms and the firewalls, to the very first person who ever tried to answer the question this whole episode is built around, in the plainest, most literal way imaginable. Isaac Newton never used the phrase black hole, and he never could have, not because the idea was too exotic for his era, but because the mathematics he built, brilliant as it was, simply did not contain the tools to describe such an object properly. Newton's law of universal gravitation, published in 1687, describes gravity as a force, a direct pull, reaching instantaneously across empty space from one mass to another. In Newton's picture, The sun pulls on the Earth, right now, this very instant, across 93 million miles of vacuum, with no delay, no messenger, no mechanism specified for how the pull actually gets from one place to the other. Newton himself, remarkably, found this deeply unsatisfying. In a 1693 letter, he wrote that the idea of one body acting on another across empty space without some intervening medium was to him so great an absurdity that he believed no one with a competent grasp of philosophical reasoning could ever fall into it. He offered the law because it worked, because it predicted the motion of planets and comets and tides with extraordinary, unprecedented accuracy, not because he believed he had actually explained what gravity fundamentally was. Curiously, in a strange, roundabout way, Newton's own mathematics came closer than he ever realized to anticipating something like a black hole. In 1783, the English clergyman and geologist John Michell, working entirely within Newton's framework, calculated that a sufficiently massive, sufficiently compact star could have an escape velocity, the speed needed for anything to break free of its gravity, exceeding the speed of light itself. Since light, in the physics of the 18th century, was thought to be made of particles subject to gravity like anything else, Michell reasoned that such an object's own light could never escape it, and it would appear, to any distant observer, completely dark. He called these hypothetical objects dark stars. Pierre-Simon Laplace independently proposed something remarkably similar a few years later. Neither man had any way to develop the idea further, no observational method to look for such an object, no deeper theory to explain what would actually happen at that critical boundary, and the idea faded into a curious historical footnote for well over a century, mentioned occasionally, taken seriously by almost no one, until Einstein and Schwarzschild picked the thread back up in an entirely different mathematical language in 1915. Why does this matter for tonight's question? Because it reveals something genuinely important about how differently gravity behaves depending on which framework you use to describe it. And it clarifies exactly what changed between Newton's era and our own, and exactly what still has not changed. In Newton's picture, gravity is a force generated directly and continuously by mass, transmitted instantaneously through space by some unspecified mechanism Newton himself was uncomfortable with. Michell's dark star, calculated entirely within this Newtonian framework, is still, fundamentally, an object made of ordinary matter, sitting at a location, continuously generating a gravitational pull the way any Newtonian mass does. There is no horizon in the modern geometric sense in Michell's picture. There is simply a star so dense that its escape velocity happens to exceed the speed of light, a difference of degree, not of kind, from any ordinary massive object. Einstein's picture and Schwarzschild's exact solution built on top of it changed the nature of the question entirely, in a way that Newton's framework was never equipped to express. Gravity in general relativity is not a force reaching across empty space from one object to another. It is the curvature of space-time itself, and mass does not pull on other masses directly. It tells space-time how to curve, and that curved space-time, in turn, tells other masses, and light and everything else, how to move through it. This reframing is precisely what makes the modern black hole question so much stranger and so much harder than Michell's 18th century dark star ever was. In Michell's Newtonian picture, if you could somehow ask where the gravity comes from, the answer would be immediate and unremarkable. It comes from the star, the same way it comes from any star. Full stop. In Einstein's picture, mass curves space-time, and once that mass collapses behind a horizon, the curvature it generates persists in the geometry itself, in the fabric of space, in a way that no longer seems to require the ongoing, moment-to-moment presence of a located, continuously acting source in quite the same intuitive sense that Newton's framework demanded. This is, in a real sense, the entire 230-year arc of this question compressed into a single comparison. Newton gave physics an equation that worked, but that he himself considered fundamentally unexplained, a description of what gravity does without any account of what gravity actually is. Einstein gave physics a geometric picture that explained, with extraordinary precision, how gravity works, tying it directly and beautifully to the curvature of space-time, but that picture in turn produced an object, the black hole, whose very existence pushes past the edge of what even Einstein's geometric picture can fully explain. Once you ask what, precisely, continues generating that curvature after the source has collapsed past the point where the word source still straightforwardly applies. And Bekenstein, Hawking, at Hooft, Susskind and Maldacena, working across the following century, pushed the question one full layer deeper still, suggesting that the true, most fundamental answer might not be geometric in the way Einstein imagined at all, but informational, statistical, entropic. Arising from the same deep logic that makes a stretched rubber band snap back, projected outward from a boundary onto the space it encloses. Notice the pattern running underneath all of it, because it is the same pattern this channel has traced before, across other episodes on other mysteries. Every time physics has pushed hard enough against one of its own foundational questions, the answer that eventually emerged did not simply patch the old framework, it reframed the entire question, sometimes so thoroughly that the original question, the one physicists thought they were asking, turned out to have been the wrong question all along, built on an assumption too basic to notice it was even being made. Newton assumed gravity required a located, continuously acting source, an assumption so natural he never even stated it explicitly, and general relativity quietly overturned it. Early black hole physicists assumed the singularity, or something very like it, must be the literal physical seat of a black hole's gravity, an assumption so natural that Hawking himself spent years resisting Bekenstein's suggestion that entropy, and by extension something like the essential physical content of the black hole, might belong to the horizon instead. And now a significant portion of the theoretical physics community is taking seriously the possibility that gravity itself, the geometric curvature Einstein handed us as the deepest available answer, might not be the final layer at all, but might be a large-scale emergent statistical shadowcast by something more fundamental still, something built out of quantum information correlation. And entropy, in a language physics, has only begun learning to speak fluently within the last 20 years. We are, in other words, standing at exactly the kind of threshold this channel keeps returning to. Not a settled answer being quietly filled in around the edges, but a genuinely open question sharpened by a century of extraordinary theoretical progress that has not yet found its Einstein. And it is worth remembering, before we go further tonight, that the person who eventually resolves it, if it is ever fully resolved, is likely working with tools and a vocabulary that would have looked as unfamiliar to Einstein as space-time curvature would have looked to Newton, sitting under his apple tree, certain only that something, somehow, was reaching across the empty air between the tree and the ground. Part 10. What the black holes we've actually seen are telling us. Everything we have discussed tonight so far has lived almost entirely in the realm of mathematics and theory, singularities that may or may not be real, horizons that may or may not be holograms, information that may or may not survive evaporation. It would be reasonable, at this point, to wonder whether any of it actually touches the real universe, or whether we have spent the last hour and a half following an elegant but untethered chain of pure thought. So it is worth taking a real pause here and asking honestly, what have we actually observed? What do we actually know with real confidence from real instruments pointed at real black holes? The observational story of black holes is, itself, a remarkable piece of scientific history, and it unfolded almost entirely within living memory. For decades after Schwarzschild's solution, black holes remained purely theoretical, objects that existed on paper but that almost no one expected to actually find sitting in the sky. That began to change in 1964 with the discovery of an extraordinarily bright X-ray source in the constellation Cygnus, catalogued as Cygnus X1. Through the 1970s, careful observations of a massive visible companion star orbiting an invisible partner, combined with the intense X-ray emission consistent with matter being violently heated as it spiraled into something extremely small and extremely dense, built a case that grew steadily stronger until Cygnus X1 became widely accepted as the first strong observational candidate for an actual, physical black hole. Famously, Stephen Hawking bet the physicist Kip Thorne in 1974 that Cygnus X1 would turn out not to be a black hole after all, a wager Hawking himself later described as a kind of insurance policy, a bet he would be happy to lose, since so much of his career's work depended on black holes being real. He conceded that bet too in 1990, once the observational evidence had become effectively undeniable. Since then, the evidence has accumulated from an increasingly wide range of independent directions, each one confirming the same basic picture from a completely different angle. Astronomers have tracked stars orbiting the exact center of our own Milky Way galaxy for decades, most famously through the painstaking work of Reinhard Genzel's and Andrea Gheze's teams, work that earned them a share of the 2020 Nobel Prize in Physics. One particular star, designated S2, completes a full, tight orbit around whatever sits at our galaxy's center, roughly every 16 years, at times moving at several % of the speed of light, swinging closer to that central object than Mercury ever swings to the Sun. The orbit only makes sense, only obeys the equations correctly, if the object it is orbiting has a mass of roughly 4 million suns packed into a region smaller than our own solar system, with nothing visible there at all. There is no other known category of object in the universe that could account for that combination of mass and compactness. Then, in 2015, came the detection that many physicists consider the single most direct confirmation of everything we have discussed tonight. The moment gravitational waves, ripples in the fabric of space-time predicted by Einstein a full century earlier, were finally detected directly by the twin LIGO observatories, arriving from two black holes, roughly 30 times the mass of our Sun each, spiraling into one another and merging over a fraction of a second, more than 1 billion light-years away. That single event radiated more power for that brief instant than every star in the observable universe combined. And the exact shape of the gravitational wave signal, its rising pitch and sudden cutoff as the two black holes merged into one, matched the predictions of general relativity with extraordinary precision, confirming not just that black holes exist, but that they behave dynamically exactly as Einstein's equations describe. And then, in 2019, came the image. The Event Horizon Telescope, a coordinated network of radio observatories spanning the entire globe, effectively turning the whole planet into a single telescope, roughly the size of the Earth itself, produced the first ever direct image of a black hole's shadow, the dark silhouette cast against a glowing ring of superheated gas swirling around the supermassive black hole at the center of the galaxy M87, some 55 million light-years away. In 2022, the same collaboration produced a similar image of the black hole at the center of our own Milky Way, Sagittarius A star, the very object whose mass had already been so precisely measured by tracking S2's orbit for decades. Both images match, with remarkable precision, exactly what general relativity predicts a black hole's silhouette should look like, the size and shape of the dark shadow directly reflecting the size of the event horizon calculated from Schwarzschild's original solution, more than a century after he wrote it down from a trench on the Eastern Front. So this is not speculation, stacked on speculation. The existence of black holes, their masses, their spins, the precise shape of their horizons, and the way they warp space-time around them exactly as Einstein predicted, all of this rests on an extraordinarily solid, confirmed observational foundation. What remains genuinely open, what remains theoretical, is everything we discussed in the parts before this one, the deep interior. The true nature of the singularity or its replacement, the fate of information, and the ultimate, most fundamental origin of the gravitational field itself. The boundary between settled fact and open frontier in black hole physics is, in this sense, remarkably sharp and remarkably well understood by the physicists working in this area, even if it rarely gets communicated that clearly outside the field. We know with tremendous confidence that black holes are real, that they behave exactly as general relativity predicts from the outside, and that the horizon is a real, physical, measurable boundary. We do not know, with anything like that confidence, what is truly happening on the other side of it, or what, at the deepest level, is actually generating the pull we can measure so precisely from here. There is one more observational thread worth pulling on before we move toward tonight's closing reflection, because it returns us directly to the entropy and information questions from earlier, and it shows just how seriously the physics community takes the idea that black holes might be telling us something universal, not just something specific to themselves. Over the past 2 decades, researchers working in condensed matter physics, the study of ordinary materials like metals, superconductors, and exotic quantum fluids, have discovered that certain strange, poorly understood classes of materials, particularly a category called strange metals, seem to dissipate energy and scramble information at a rate that matches, with startling precision, a theoretical bound on how fast a quantum system can possibly scramble information. A bound derived directly from black hole physics, and specifically from the same holographic reasoning we spent 2 full parts unpacking earlier tonight. Physicists studying these materials in laboratories using nothing more exotic than carefully cooled crystals and electrical probes have found themselves reaching for the mathematics of black hole horizons to explain what they are seeing, not because they expected any connection between a chunk of metal on a lab bench and a collapsed star billions of light years away, but because the mathematics. Developed originally to describe the most extreme gravitational objects in the universe, turned out to be exactly the right tool for describing some of the strangest, most poorly behaved materials here on Earth. That convergence, gravity's most exotic objects, and condensed matter's most poorly understood materials, turning out to obey the same deep mathematical structure, is precisely the kind of clue theoretical physicists live for. It suggests that the holographic, information theoretic picture we have been building toward all night is not simply an elegant story invented to patch over an awkward gap in our understanding of black holes specifically. It may be a genuine, deep feature of how information, entropy, and geometry relate to one another throughout nature, appearing wherever a system pushes hard enough against its own fundamental limits. Whether that system is a dying star collapsing past the point of no return, or a thin, carefully grown crystal sitting quietly on a laboratory bench 3 feet from a physicist's hand. Part 11. The question underneath the question. We have now walked slowly and carefully through nearly every layer of this problem that current physics actually has access to. It is worth taking stock, gently, before we move toward the final part of tonight's episode, because the honest shape of what we do and do not know here is itself something worth sitting with in the dark. We know with total observational confidence that a black hole's gravity measured from outside its horizon is real, precise, and exactly as strong as general relativity predicts it should be, given the mass, spin, and charge of the object. We know this from the orbits of stars circling the center of our own galaxy, from the ring-down of gravitational waves detected as black holes collide, from 2 direct photographs of black hole shadows taken 5 years apart, matching theoretical predictions made a full century before either photograph was possible. This part of the story is not speculative. It is among the most thoroughly tested predictions in the entire history of physics. We know, with almost equal confidence thanks to the no-hair theorem, that whatever detailed history and structure the original collapsing matter once had is from the outside completely erased, leaving behind only 3 surviving numbers. This is a rigorous, mathematically proven consequence of general relativity, not a speculative add-on. We know, from Bekenstein and Hawking's work in the 1970s, confirmed and extended by decades of subsequent theoretical work, that black holes carry real physical entropy, that this entropy scales with the area of the horizon rather than the volume of the interior, and that black holes therefore behave in every measurable thermodynamic sense as genuinely hot objects, slowly radiating themselves away. Beyond that point, the ground becomes genuinely open. We do not know, with anything approaching the same confidence, what the interior of a black hole actually contains. We do not know whether the true, deepest description of a black hole's gravity is better understood as something still located inside, however strange that interior turns out to be, or as something more fundamentally encoded on the boundary itself, in the holographic sense that Susskind, at Hooft, and Maldaceno's work suggests. We do not know whether Velindi's proposal that gravity itself is a fully emergent, entropic phenomenon, arising the same way a stretched rubber band's tension arises, will ultimately survive the technical challenges raised against it, or whether some more refined, more rigorous version of that same basic insight will eventually take its place. We do not know, with total certainty, exactly how information genuinely escapes an evaporating black hole, even though the balance of evidence over the past decade has shifted decisively toward the conclusion that it does escape rather than being truly destroyed. And underneath all of these specific open questions sits one more, quieter, and in some ways more unsettling than any of them, because it is not really a question about black holes at all. It is a question about what kind of thing an explanation is even allowed to be. Because notice something about the entire arc we have followed tonight. Every time physicists have pushed one layer deeper into this problem, seeking the true, final, physical source of a black hole's gravity, they have not found a located object sitting patiently at the bottom, generating the pull the way the sun's matter generates its pull. They have found, instead, another layer of description. Mass gives way to curvature. Curvature gives way to horizon area. Horizon area gives way to entropy. Entropy gives way to quantum entanglement, to correlations between particles, to the statistical bookkeeping of how information can be arranged. At no point in this entire chain has anyone found a bedrock layer where you can finally point and say, there, that is the actual physical thing doing the pulling, full stop, nothing underneath it. Each layer, so far, has turned out to be a description of the layer above it, translated into a different mathematical language, and it remains a genuinely open question, argued about seriously by working physicists, whether this chain of translations ever bottoms out at all, or whether it is translations all the way down. This is not a failure of physics, and it is worth being careful not to hear it that way. It is, in a very real sense, the opposite. It is what progress in fundamental physics has always looked like at every stage where a truly new layer of reality has been uncovered. When physicists first learned that heat was not some invisible fluid, but was, instead, the collective motion of countless individual molecules, the concept of temperature did not become less real. It became explained, revealed as a large-scale, statistical description of something more fundamental happening underneath it, something no single molecule, on its own, could be said to possess. A single molecule does not have a temperature. Billions of them, moving and colliding, produce something that behaves, at the large scale, exactly like a temperature, real, measurable, and thermodynamically consistent, even though it is not, in any simple sense, sitting inside any individual particle. If gravity is undergoing the same kind of transformation right now in the hands of the physicists working at exactly this frontier, then the honest answer to tonight's opening question may turn out to be something genuinely strange to sit with as you drift towards sleep. A black hole's gravity does not come from its singularity, because the singularity, in all likelihood, is not a real physical place at all. But the sound general relativity makes when it is pushed past the edge of its own validity. It does not come from the horizon either, treated as some special isolated source, because the horizon itself may be better understood as an encoding, a description, a boundary condition, rather than a generator. It may, in the deepest sense current physics can offer, come from information, arranged, correlated, and counted according to rules we are still only beginning to properly formulate. Rules that seem to connect the interior of a collapsed star to the behavior of exotic crystals on a laboratory bench, to the geometry of space-time itself, to something that may not, at the very deepest level, be gravity at all, but something else entirely, of which the gravity you have felt every single day of your life, holding you gently to the floor, is merely the shadow, cast outward from a boundary you can never directly reach or see. We are, quite genuinely, waiting for the next Einstein on this one, and it is worth remembering, one more time, that when that answer finally comes, it may look as unfamiliar to us tonight as curved space-time once looked to Newton, certain only that something, somehow, reached invisibly across the space between his hand and the falling apple. So here is what you actually know now, lying there in the dark. A black hole has no surface, and yet it pulls exactly as hard as the star that became it once pulled, decimal point for decimal point. Its entire history, everything it once was, has been reduced to 3 surviving numbers. Its gravity may not live where you think it lives at all, not at a singularity, not even at the horizon exactly, but somewhere closer to information itself, correlations counted and encoded, the same quiet arithmetic that may be holding you to the floor of the room you are in right now. Newton felt gravity and called it an absurdity he could not explain. Einstein gave it geometry. Bekenstein and Hawking gave it a temperature. Somewhere out past all of them, unfinished, is the person who will finally say what it actually is. You are not separate from any of this. You are made of the same information, the same entropy, the same quiet bookkeeping the universe performs on every particle it has ever held. If you want more nights like this one, spent chasing a real mystery all the way down to the edge of what anyone knows, subscribe and come back for the next one. Sleep well. The universe will still be pulling on you in the morning.